Welcome to TypeScript tutorial 0 to Hero. I'm Matthew and I've been using TypeScript for several years. I finally decided to create a roadmap that will fully cover all needed topics to use this language effectively. As a follow-up, I prepared this comprehensive tutorial that will guide you from the very beginning, even if you don't know anything about this language, all the way to understanding proper patterns and setting up your application's configuration. There are several prerequisites you need to meet before starting this tutorial. I will assume that you have a basic understanding of JavaScript. During the practical parts of the tutorial, you'll need a code editor with TypeScript support. On the video, I will be using Visual Studio Code. This is the first part of the tutorial, so we will be focusing on basic types. They are the fundamentals of every more complex system. Then we will go through function typing. Next step will contain ways to define the shape of an object, types and interfaces. We will cover the most important TypeScript keywords as well. At the end, I will discuss quickly using enums in the type system. The roadmap you saw in the background is an interactive tool. You can find and pick topics you are most interested in. I'll be following all the proposed steps one by one. With an account, you will get updates if there will be new features in upcoming TypeScript versions. I posted the link to the roadmap in the description of the video. Let's get started. We need to start by learning basic types that are present in the TypeScript. We'll use them to build more complex types in the future. JavaScript has a few primitives that have a corresponding types in the TypeScript. The string will mark a text-based value. Number will accept both integer and float, which is basically how the JavaScript is handling all of the numbers. For true-false values, we'll use Boolean type. For a variable that contains null, we can use it as a type. The same happens with undefined. There are also a few more exotic primitives, symbols and begint, but they are rarely used, so we will not focus on them. Sometimes the variable can accept a list of possible value types. To declare such a type of variable, we will use a union type. To create the union, we use the pipe symbol. For example, here we have a variable that will accept both strings and numbers. Another variable will accept strings, but also null. We can use a string, number, or boolean to create a type that will accept only specific values. Here we have an example of a variable limited to two specific strings. Next, variable that will accept only true or null. The last example is a team ID, where we expect to have only 1, 2, or 3 as a value. To represent an array containing a specific type, we have two options. We can use either square brackets or an array template. Compare the difference in the syntax of both methods, especially when the array contains union types. When dealing with arrays of a constant size, we can use tuples to represent type of each specific index of the array. The concept will be more clear on an example. We have an array that contains only two items, number and a string. If we use standard array type, each index will be treated as a number or a string. We can use tuple type to determine that the first index is always a number and the second is a string. This will also prevent us from accessing indices outside of the boundary. I'm glad that you made through the first part of theoretical presentation, and this is the second part of the tutorial that we'll be doing in parallel. So I created a repository that is containing all of the transcripts of the topics that I'm covering during this tutorial. So it contains all of the topics, all of the code examples that you see during the presentation. You can go ahead and copy the TypeScript code that is here and play around with it or investigate it even more. And you can clone this repository from the GitHub, but what is most important about this repository is that I created an exercises that you can do after each of the theoretical part of the tutorial. So just to solidify your knowledge or check if you understood correctly the concepts. So you can pause the video now if you'd like to and do the exercise for the basics type by yourself, or if not, let's follow me and let's see how we can use the knowledge in practice. So don't be scared that the files that you will open in IDE will be marked as incorrect. That's an intentional thing. We're gonna fix a few things around the types in these examples simply just to create the example of proper type system. And at the start I will remove this type as this is intended to be replaced in every example. So we'll see every place that it's needed to be replaced. So I will start with the first example, and here the idea of this example is to replace the fundamental types for each of these variables. So for the price we have some kind of number, so of course it will be a number. For total sum, this is the text, so we are gonna expect it to be a string. Here we've got a random number generated, we are comparing it, so it will be either true or false. So here it will be a Boolean value. And some of these examples will not really make sense when it comes to the code itself. They are about the typing, so don't be scared that some functions will have some kind of dummy implementation and console logging the arguments. The idea is simply to get into the typing and the habits of proper type system. So here we've got a value that is null, so the type will be also called null. And for undefined, the same way, undefined type. And this example was simply to get into this idea of typing the variables, but as I said, in the most cases you do not need to do this. The TypeScript will infer the value for the variables based on the initial value. So here we've got the price, and it's especially like even marked with a specific value as its const value. If it would be a let variable, then it would be marked by default as a number. The same here. If it would be marked as total sum, the specific variable, because we are not expecting it to be changed. If we would define it by let, it will be marked as string as we did it before. Here we've got the Boolean. Here, no matter what we're gonna do, this is it's calculated during the execution, so it will be always a Boolean. We don't know if it's true or false. And here as well, no need to define it as null or undefined. Everything will be properly typed. And this is another hint: use your IDE. It will help you to understand what kind of value is expected for each of the variables. Do not type everything that is needed, but for now, let's type everything so we'll get used to typing. So the first example is over, so let's go to the next one. Here, this example is focusing on the union types. To just a small reminder, union types can accept a range of specific types, and we create it using pipe symbol. So for the first example, we have a random check, and it will return either a 10 as a string or number. So let's type it as a string, Let's type it as a string or number. And yeah, now it's correctly typed. The second example, okay, so we have a user age, we assign it a number and undefined. Let's add this kind of typing, and see, we've got an error, so we missed something. And when we go over the error message, the TypeScript will tell what's going on. So we are trying to assign the null, like initial value, null, but we expect number or undefined. So we simply missed another option for this tuple. So it will be a union. So it will be a null. Okay, so the third union, it can be either a string, so no union type, or we can use this specific, if you are expecting this specific values to be here, so it could be either up or down. And as in the previous example, we do not really need to do this. For this particular value, it will be either 10 or 10. if we would define it as let, it will be a string or number. This is how we defined it previously. But yeah, this is how we are supposed to leave it in our code, because let's allow to TypeScript do its work where it can. For this one, we can't really remove this one, because if we would, the inferred type will be a null, and we will not be able to assign a number or undefined to this. So sometimes we need to specify the variables, but in most cases not really. And here as well, if I would remove this one, this would fall back either up and down. If it will be let, it will fall back to the string. So here I would do it like this, I would do it like up or down. If I would consider it like to be this specific type using the values. Yeah, but no need to define in most of the cases. So we went through the union types. Let's focus now on the arrays. So I will start with the bracket syntax. So here, okay, we've got an array containing strings. So easy peasy, string. Here we've got an array that contains numbers or null. So I will use the union type to define that the shape of the item is either number or null. And again, I'm expecting an array, so I'm adding the brackets. Here I can either use string array, or if these values are some kind of specific type, like we can use also the union types. So I'm copying it. Let me replace the commas with the pipe symbol. And here, for example, of course, we can extract this type, so we can create some kind of to-do item type. No need for brackets here. And then we can reuse this type to simply create an array of specific type. As I said, there is a second option to define the arrays. So let's use the array keyword, and it will be array of strings. Here the same, it will be array of number or null. Here, as you see, we don't need to add the brackets. So this is like some people prefer to use array because of this. So it's easier to work with union types then. And here it will be an array containing to-do item. Of course, we need to remove the brackets at the end. So yeah, we covered the arrays types. And the fourth example is a little bit more challenging. So this example is all about the idea behind tuple type. So let's say we followed my advice that let's TypeScript to infer the definition of the variables. If I would do this like here, then the result type would be considered as an array of string or number. And when we destruct it and then use the specific values, the 0 item and the item number 1, no, it's not really working for us, because the TypeScript is expecting that it can be either a string or number. So I cannot really execute to lowercase, for example, for the number 1. But as we are defining this constant size array, we can use tuple to define what kind of result we are expecting. So if we know that the array will always contain 2 elements, and the first one is a string and the second is a number, so we can use this tuple type to define specific shape of result. And now TypeScript will know that the element 0 is string and element number first, like on the index 1 is a number. So everything works fine here because the TypeScript knows exactly what kind of username and age type are. So the next examples will be much more challenging. The first one was to simply get you into the mood of typing, and we'll follow up now with the functions. TypeScript is analyzing the most probable type of variable by looking up its initial values. For most of the cases, we don't need to help TypeScript at all. So there is the question, when exactly we need to define the types? Definitely for the arguments of the function. As developers, we need to define what kind of inputs is expected and can be handled. Let's begin with a function that returns a number. We can define a general type for this function. When we proceed to implement a function of a specific type, TypeScript will automatically check if it matches the expected type. There is no need to explicitly specify the type of the function. Instead, we can simply provide inline argument types. Sometimes we might also need to add the type of the returned value. In the next example, we'll explore a function with a single argument. A helpful tip: when creating a function type, we need to provide a name and a variable type. This name can be entirely different in the implemented function, and it will still conform the defined type. Once again, we don't have to create a separate type declaration. We can conveniently specify the argument types inline and then proceed with the implementation of the function. A function can have multiple different arguments. In this case, we follow the same approach. We define the type of each of the arguments and the expected return value. By the way, when we annotate a lambda function with a specific type, TypeScript will automatically infer the argument types. Here we have an example of the same function defined inline, without relying on a previously created type. Sometimes some arguments can be optional. To mark an argument as optional, we simply use a question mark before specifying its type. Once again, here is an inline implementation of the same function. It's valuable to understand the various ways types can be applied, but in general, the most convenient way to type a function is by specifying its argument types inline. Optional arguments become particularly interesting when we wish to assign a default value to them. When defining the function type, we still mark a variable as optional. Just as in regular JavaScript, we set a default value for the variable within the function definition. When a default value is provided, the variable is no longer considered optional inside the function body. This allows us to work with it without concern of potential undefined values. For comparison, here is the inline definition of the same example. By default, TypeScript would treat the action variable as a string, so we manually define its more precise type. In the provided code examples, I was showing only lambda functions. The same rules applies for the classic JavaScript functions, which are defined using the function keyword. We define the variable types and sometimes, when it's needed, return type. In TypeScript, there are two specific return types for functions. The first one is void. This return type indicates that the function is not expected to return anything. For clarification, we could potentially define the return type as undefined, but in various TypeScript versions, it would require from us an explicit return statement inside the function body. The proper approach will be to mark function as returning void instead. When we are not returning anything, there is no need to explicitly mark the return function as void. TypeScript will properly infer return type by itself. The second specific return type for a function is never. This signifies that the function will never finish. A common example of such a function would be one that is always throwing an error or contains an infinite loop. This return type is relatively uncommon in practice. As I emphasized earlier, when declaring functions, whether using lambda or classic syntax, we typically don't need to specify the return type. TypeScript can automatically infer it. There are two exceptions to this rule. The first exception is the case of a recursive function, where the return type depends on itself. Therefore, we must assist TypeScript in defining it. The second situation is when the return type must be more specific than one that is inferred. Here we have an example of a function that, by default, will be treated as returning a string. However, we intend to return a union containing two specific actions, so we manually define return type. In JavaScript, some functions can accept an unrestricted number of arguments. These functions are defined using the spread argument. And in TypeScript, we can also specify and handle this type of argument safely. The spread syntax is typed using an array type. This feature allows us, for example, permit an unlimited number of arguments while still checking if at least one of items is provided. The next example demonstrates a spread argument with items of different types. We are not limited always to having all of the arguments defined as a specific type. In TypeScript, there is no async keyword. To designate a function as asynchronous, we need to encapsulate the return value within the promise utility. When defining a function that doesn't return anything but is asynchronous, the proper return type is promise void. In most cases, the inferred type will be valid, so there is no need to define return value for inline functions. The next example demonstrates a function that will eventually return a number. It is important to remember to include the promise wrapper when we are manually adding return type. Omitting it will result in type error. Once again, we face the same question. If TypeScript can infer function types accurately when we define them, why do we need to emphasize proper function typing? The answer is the same as the reason for understanding basic types. Functions can serve as arguments for other functions. These callbacks need to be properly defined so that our code is checked for every input case. Let's explore some callback examples. We'll begin with a function that accepts a callback returning a string. Within the function body, we can call the callback, knowing that the result will be a string value. Callbacks can, of course, be more complex. Here we have an example of a function that requires an input and returns a promise with either a number or null. Again, thanks to proper function typing, we know how to handle the response correctly, such as remembering to add the promise, which is something that I always tend to forget. The last example features a callback with an optional argument. We should only define callbacks with optional arguments if we are passing that optional argument conditionally. If it isn't the case, let's make the argument required. Callback argument types can be a bit tricky. The passed function doesn't necessarily need to be the exact same type as the expected argument, but must fulfill its requirements. Execution, which is based on the expected type, must be safe. Let's consider an example type, a callback that requires a number or a string as the first argument, and an optional second argument that will accept an array of numbers. The callback is marked as returning void, so we don't expect any return value from it. We can pass a function that can accept a broader range of argument types as long as it supports all the required types. Argument x can also be null, which isn't the problem, since we don't anticipate passing this value inside the callback v1 function. We will pass either a number or a string, both of which are supported by the passed function, so we are safe. It's not an issue if the passed callback returns something. Inside callback v1, we aren't expecting the callback function to return anything, so the function can still be used as an argument. We will simply ignore return value. If the passed function expects more arguments, but additional arguments are optional, we can still use it as an argument of the callback v1 function. We simply rely on the fact that when calling the function, these additional arguments can be omitted. The same situation applies to a function that accepts fewer arguments. We will pass them to the callback, which will be called inside the function body, and they will be simply ignored within the CB function. This way, functions will be executed correctly and safely, which is what the TypeScript is aiming for. We have explored different types that can match callback function. Now let's examine a few examples of functions that cannot be passed as proper arguments. Consider the callback v2 function, which expects to receive a function with two arguments, the first accepting either a number or a string, and the second accepting an array of numbers. This function should return either a string or a number. Here we have the first example of an invalid function. Since the x argument can only accept a number, this function will fail if passed into callback v2, as it can be executed there with unsupported string as a first argument. The second example demonstrates a function that returns a wider range of values than expected. Since failing type 2 can return null, this value would not be properly handled inside callback v2, resulting in TypeScript error. Of course, if the pass function expects more required arguments than specified within the callback type, this would also trigger a TypeScript error. Inside callback v2, the function will be executed with only 2 arguments, which is invalid. These examples of accepted and invalid callbacks should help you to build understanding of how matching of the function types works. Okay, so we are after the theoretical part about the functions, and let's focus now on more practical aspect of typing them, and let's go through the examples that I prepared for this tutorial. Okay, so as in the previous example, I will start by removing this unknown type, simply to see what kind of things we are missing from the examples. And let's start with the first exercise. So this exercise is about creating the type that will define the shape of the test function. And let's focus how this test function is supposed to be called. So we see this is the function that is called on 2 arguments. The second one, as we see, is an optional. The first one is, it seems that it's accepting the strings, and the second one is an optional and it can accept either a string or null. So let's define this type of function. So the first example, the first argument will accept string, the second argument is optional, and it's accepting either string or null. What about the return type of the function? We are not really expecting any return type. We are not using the return type anywhere. So this is probably a function that is not returning anything. So void. And as we see, there are no complaints about the types here. So I think we are done with the first example. Okay, the second example is about the definition of the arguments and return type of the specific function generate numbers. Okay, and we have a hint that generate number should return only 0 and 1 values. Okay, so we see that when we are calling generate numbers, we are calling it with the number, and it would make sense to type this argument as a number. So we are creating an array of the specific size. Then we are filling it with random values, either 0 or 1. So the return type is an array. So let's start with array. I will use the array syntax, not the brackets. And we know that each item is either 0 or 1. Okay, so this is fixed. And here, as I wrote in the comment, we are expecting the error because the values will be 0 or 1. So never in code we are expecting this item to be compared to number 2. So this part of the code does not really make sense. Like, it will run nicely, it will simply never go into. So the TypeScript is warning that something in our code does not really make sense when it comes to options. If we were typing this generate number as a function expecting to return also number 2 or even return any kind of number, everything would be fine. Okay, so I think we are done with this example. Let's proceed to the next one. So here the first idea is to create the proper typing of exercise 3 type, and then after we deal with it, we'll simply remove this type and go into the inline function definition. Okay, so let's look at the execution of this function. We see that the first example is always the list of strings, but we have also a second argument which contains a default value also appearing to be a string. So here, if we were talking about the type of this specific particular function, so the first argument, as we saw, is the list of strings, and the second is optional string. Okay, what about the return type? So this function is checking if any item is containing this optional but passed with the default value Alan string. So we are checking if any of these strings contain the particular string. So this is a check. So we are expecting to return a Boolean value. So we're either return true or false. So Boolean. Okay, so here, what is the expected outcome of these calls? Of course, Boolean, the same as we defined here. Of course, as we are talking about this multiple times, we do not really need to specify this. This is purely for the exercises. TypeScript would definitely infer the return type with ease. So like I'm saying, in the real code examples, do not type everything, simply the stuff that needs to be typed. Okay, so we have the exercise 3 type function definition, but let's recreate it with inline function definition, which is much easier to work with. And this typing is simply getting us ready for proper callbacks typing exercises. So the first argument is always be a string array, and as the inferred type for the username will be a string based on the default value, we don't really need to write like this here. It's not really needed. The default value will provide a proper infer type. And here we go. So as you see, only one type that is really needed here. Okay, so let's go with the next one. And the idea of this exercise is also to define the proper exercise 4 type. These two functions are not really important. They are some kind of dummy helper functions that provide some kind of return value that we can work with. Okay, so exercise 4 type. This is the function. Okay, let's see how it's called. So we expect to pass some kind of URL. This is a string. And then we pass some kind of action, but optional, post or get. So probably here we will be having the first argument. It will be a URL, so string. The second is an optional action. It could be a string, but let's be more specific here that we accept either get or post. Okay, so what is the return type? This is important. The function is asynchronous. So the return type will be a promise. But what will this promise eventually resolve to? Looking at this implementation, we don't really know what this response is. So let's use the infer types from the TypeScript. Okay, it's helping us. It's saying, okay, that will be a promise of a string. So this will be a string here, but as I said, not really needing to do this. Just simply allow TypeScript to infer the return type. It will be string here. Here as well, we could say it will be finally awaited as a number. Everything's fine. But in real code, we don't need to do this. The TypeScript will correctly mark what kind of return type it is. So we have a string, number, or null, eventually resolved. So it will be inside the promise string, number, null. Yeah, so when we define this type of function, we don't really need to define the return type. And here as well. What is this? This is not really awaited, so it will be a promise of this kind of values. And here, as you see, maybe it will be helpful because maybe we forgot to await this and we would try to work on these values. The TypeScript would warn us that the value is a promise, not a string or number or null. So this is how the TypeScript is helping us to code faster and simply make less mistake. Maybe not on the production, but during the development. So you don't need to roll back to the changes. See, okay, I missed this one. I forgot to handle null. It's really helpful. Yeah, and let's also remove this exercise 4 type and type this function with inline inline type. So here the URL will be a string. Or maybe one thing that I can mention here, no matter what we type here, the function will match the same function. So it can be either X, but we can be much more specific. We can call it URL and call this as an action. And now it will be much more helpful for us when we are trying to use this exercise for type. So when we are creating these function types, if we can be more specific about the naming of the arguments, let's go with more specific names, simply to boost our productivity. Don't trying to analyze the code to get what kind of value is it, because a string can be either URL, the name, whatever. Just let's leave some hints in the type system as well. So the first URL will be a string. Here, as we're expecting a specific type of actions, I'm gonna use it. And of course, here it's not optional because we have the default value. So it will be like this. And as I said, magic happens. We don't need to analyze the code to get what is the return value. The TypeScript will infer it correctly. And we should really rely on this tool in this case. Okay, so the fifth example. Here we have a function that we're gonna try to type the return type. The problem with this function is it's referring to itself. So this is the example of the function where return type cannot be inferred by the TypeScript because of the nested types, this circular dependency. And we have a tip that to specify the arguments, we may consider using like an helper type. So as you see, this example is trying to use the idea of reference functions. So the structure that we can pass is also a little bit complex. And the idea here is that it can be an array that contains items that can be strings, but also the same type. So nested arrays of strings containing arrays containing nested arrays of strings and stuff like this. So how the type would look like? Okay, so we have a type like helper type. And this type can contain strings, but also can be an array containing more nested things. So it will be a string or helper type array. And here we have also the spread arguments as from the previous technical, more theoretical part. We know that to type the spread array, we also need to use array type. So we use this help type with an array. And here it is where we need to specify the return type of the function. So what we are really doing here is counting nested items of the arrays. So counting is returning a number here. So we are expecting a return type of number. And here we've got another function that is like using reduce. In most of the cases when we pass like string or number here, the TypeScript can reduce what kind of result it should be. So we can like remove this types here. And if you would hover, okay, so result should be a number and the item will be an item from items. So it knows it will be a helper type. And as you see here, when we're checking for the array of item, here the item, we know it's like an array of helper type. So we can be passed with success to another layer of count items. So this example was focusing mainly not maybe on the self-referring types, but the idea that this count items function needs to return a number. So for the exercise 6, we are trying now to create proper callbacks for the functions. So the callback will be a function called with a function. So we need to take care of how this function is executed. So this is exactly the way that we are trying to define properly the initial function type. So this was preparing us to properly type callbacks. So the callback will call on the first argument a string or number, and the second argument is optional and optional number. So x will be a string or number, and the second argument is optional number. Of course, then we need to look what the function is supposed to return, and here we are not really care about the return type. So we are not really using the return type of this callback function, so it will return void. And as you see, I could potentially like remove this optionality here, but the TypeScript would complain. I could potentially like allow null to be passed here, and like TypeScript will not complain about this one, but does it really make sense? Not really, because now we need much more stricter function, and we will not use this null value here. So when we are typing the callbacks, let's be more general than specific. If we don't need this type of argument, for example, to be handled, let's not limit ourselves to it. Okay, so first example of the callbacks done. Let's proceed to more challenging one. For the second callback function, we see, okay, so we have a callback. It's called on the number and optional boolean. Okay, so we know the first argument will be a number and the second is an optional boolean value. Okay, what about the return type? As we see, we are expecting some kind of user with company. We're comparing to the nulls. So let's assume that's maybe an object or null if these IDs do not exist. And we are awaiting this. So that means that the function needs to return a promise. So it will be a promise with some kind of object, let's say just a simple object with no, like we don't need to specify anything here. Okay, so you see that TypeScript is complaining. Why it's complaining? It's complaining because await expressions are only available in async functions. So it will even like help us. Okay, I need to add async function. And what about the return type? As previously, we don't really need to do this. Like if you remove this and hover the function, we'll see it will be either a promise returning okay or undefined. But if we would analyze the code and type it like this, okay, but as I said, we don't need to do this. If we would change this implementation to some, then it's not returning proper type. The question is what we really want to have. Is it like really expected return type, or we're just copying and creating a boilerplate? Maybe we can like skip it like this, and then the function will know it's a promise sum undefined. And it really depends on the context. I will cover it in the last part of this tutorial with talk about some patterns and general approaches that you can have, like consistent approaches to the type system in your code base. So the last example is about creating this generic type for the function that would accept a specific functions in it. So trying to create a general function type. So let's start with properly typing the return types. Of course, we could remove it, but for transparency of this example, let's add this type so we can clearly see what kind of types are we expecting. So for the first functions will be argument number or string, returning string. Second function simply returning string, and the third function, okay, so we've got math min, so it will be a number or string, so the return type is string or number. Okay, so now we see that we are defining the test function that will accept each of these three functions. So we need to create a generic type for the callback that will be compatible with like three of these functions that we expect to pass here. So what we can start with, just simply creating a void function. And let's see, okay, so at the start we see that there is some kind of problem with this function. Maybe it is not the best one because we are not really taking anything, like not really taking care about this function inside the test function, because if we had some kind of execution types, we could be more specific about this one, but let's simply focus on the generic approach to defining the type that will match these three functions. So the first argument is here is number or string. Here is whatever we need. We can pass anything. This function will handle whatever we pass it here. And this argument is expected to be a number. So what is the intersection of these options? So intersection of number or string, or anything. Of course, it will be a number. So the first argument is expected to be a number. And as you see, everything is fine. This is where we could stop, depending, of course, what the implementation of this dummy test function would be. But let's be more strict about the implementation. Okay, so the second argument, here it can be whatever we want, because it will be simply ignored by the F1, by F2, of course, also ignored. So we can use this specific type from S3 as our type for the third argument. Of course, as I said, it would really depend how it's called inside test function. And this function does not really need to be so generic with the void return type. Here we have a string, here we have a string, and here we have a string or number. So really our code should take care of the callback that would return either string or number, and will be fine. But as I said, this would really depend on the implementation of test function. We should focus, this was maybe done from the opposite side. We should not really think about what we are gonna pass there. We should really think of how we are gonna execute the functions. But for the sake of trying to think of how the generic types and matching of the types function works, this was the 8th example. So I hope you found it helpful and you feel now that function typing is not a secret for you anymore. So then we'll proceed to the objects. In JavaScript, apart from primitive values, everything is treated as an object. That's why it's essential to master the typing. More complex applications always depend on extensive object structures. The syntax of the object type closely resembles how we create objects in JavaScript. We define the keys, but instead of values, we provide the expected types. For clarification, there is a second option to define the shape of an object, an interface. Switching between them requires only minor changes in the syntax. I will cover the differences between two methods a bit later. For now, I will mostly use types in the following examples. The first example showcases a simple object type. We define an author type with a keys such as name and surname as a string and age as a number. The keys can be optional, and we indicate this by marking them with a question mark. Please note that using a question mark is slightly different from typing as a tuple containing undefined. The second object type is expected to include the key, but with an undefined value, not a non-existing key. From a code perspective, it's almost the same, but the TypeScript is attempting to cover some edge cases. It is also perfectly fine for some keys to be functions. In our object type, we are only accepting keys that are numbers, strings, and symbols. We can create a type that accepts generic objects, not knowing their exact keys, but knowing their value types. Generic types can be established using an index signature. Another option is to use the record utility type, where we define the type of the keys and their corresponding value types. In the first example, we define a type that accepts objects with string keys and Boolean values. In the second object type, we are accepting objects with number keys that contain strings. Generics also prove beneficial when dealing with repetitive types. Consider the following example. We have a handler type that can implement a function of several REST methods. To solve this, we can utilize union types. They can be used as indices inside index signature. Union types can also be passed as the first argument of the record utility type. Here's how we would implement this. To make keys optional in the record type, we can wrap it with partial utility, which we'll be covering in more details later. Let's explore some more complex examples. We can combine multiple index signatures as long as they don't conflict with each other. In this example, we have a standard key definition for ID, but we use action type union to define optional functions. Feature keys will be expected to contain booleans. We can specify particular keys more precisely within the index signature, but only when the values are compatible, as seen in the example. We can add string and number keys, but not boolean, as it doesn't match the general key type. We can mark fields as read-only using the read-only keyword. Be aware of the fact that it is only checked during the code analysis. That means defining a property as read-only is not transpiled to JavaScript object-defined property with writable false. Read-only keys are more strict than standard one, so we should be really cautious when using this type, as standard objects will not match this. Sometimes we have some complex object type and need only a type of a specific key. Type lookup syntax comes with a rescue. This is especially useful when we need to reuse part of the type from a library that is not exposing its internal types. One detail: we need to access object using rectangle brackets. JavaScript dot notation will not work here. When using union and intersection on object types, the final type is more complex to analyze than primitive types. When intersecting types, you need to think of this operation as finding a common type that will be compatible with both types. So, unique keys must stay the same, while shared keys must be an intersection of them. It is easier to understand by looking at some examples. The first example shows how common keys result must be compatible across intersected types. Here, the name key must contain in result a string, as it's an intersection of string or number from type A with optional string from type B. The second example shows what happens when we are intersecting incompatible types. We have type A requiring name to be a string, while type B requires it to be a number. Of course, there is no object that will satisfy both conditions. So the TypeScript will create a result type with name as never type. Trying to create such a variable will result in error, as this is impossible to achieve. What happens when intersected types have some unique keys? We must think of this situation like this. If one of the types requires some key, that key must be present in the result type. Like here, type A contains surname key as a string, while type B contains age as a number. The result type will contain both of the keys. We can also think of this with another mindset. As type A does not specify age key, it can be optional and anything. The intersection of anything with required number, it's the requirement from age key inside type B. The result is of course the required number. This is the second way to think of intersection of the object types. The union operation has different results. It is important to remember that the union basically says that the variable's type must match one of the types in the union. So if you look at the key level, the result may be different when looking at the whole object. As before, it is easier to understand with examples. When we are using a union type, looking at the specific key without context will have a result, as we were checking what each type can contain inside. In this example, the name key will be expected to be either a string or an object. The ID key cannot be accessed as its value is not defined in all of the types. The same will happen when we are trying to use object destruction syntax. In the second example, we have two actions. The lookup result is, as in the previous example, showing two possible outcomes. But something interesting happens when we are checking the action key. In this if branch, the TypeScript can deduce that if the action is posed, then the body variable must be corresponded to type A, not the default union, which was the case before the check. We will focus on this way to narrow object types in the next part of the tutorial. Remember that union represents different possible accepted types, but once we know which of them we are dealing with, TypeScript will narrow it down. Of course, we must remember that we are talking about the whole object, not only its keys. In this example, each of the present values could be the key of the union type, but combined, they do not match any expected type. TypeScript will properly show an error. There are some edge cases I want to mention. There is no problem to pass an object containing additional keys, as long as it matches the required type. However, when we are manually creating an object of the specific type, the TypeScript will complain about writing additional keys. This makes sense, as we are in full control when we are defining objects on our own. Why would we need some additional keys of this specific type? However, this applies only to manually added keys. We can use, of course, spread operator, even if the result is an object containing some extracurricular keys. Okay, so we're back with the exercises. Now we'll be working with objects. Let's go to the examples that we have prepared for this one. Okay, so as previously, I will remove this unknown variable just for the sake of knowing where to fix stuff. The first exercise is about defining the author type to match the following types. Okay, so we're gonna need to create an object type that will accept both combinations for both objects that we have here. So we have a key name, and as we see, it's either a string array or a string. So the name will be string or string array. Nice. The next one is surname. We see it's generally a string, so let's type it as a string. Value. And now in the first author we have an age, which does not exist for the second one, so this is an optional number. And the next author has a title key, so it's a string, so it will be title as a string, but optional because it should not exist for the first author. Okay, so we created a type that is accepting, and that is proper for both of these objects that we have defined underneath, and we are done with the first example. Let's go to the exercise number 2. Okay, here we have to define the handler type, and this is an object containing one function that is a handler, and we need to specify the type of a function here. So it's not really about the objects, but it's rather a function. Just a reminder, there's no problem that some of the keys of the object will be a function. So now let's look at the function. So we see that we have the required first argument as a string in both examples. So there is a response as a string as a first argument required. And we have the context, which is like optional anything. So we mark it like optional anything. And what does this function return? The first one is returning a string. The second is not expected to return anything. So maybe for sake of this example, it will be a void, just for the sake of compatibility between these two handlers. And we are done with the second example. Okay, so now it's time for the third one. Okay, we have to define the translation mapper. Okay, how is this variable used in this function? Okay, so we know that the mapper is called on the key, so it must be an object. And it must to have like generic key string. Okay, so this example is definitely looking like an example on generics types. And then whatever we call it, we need to call it on the specific language. So we are limited only to the language keys. Okay, so this is looking like a generic inside the generic, but the second one relying on the top, on the union. Okay, interesting. So what does this function should do? Okay, so this is a translation. So probably we would like to translate it back to the string. So let's assume the return type should be a string. Okay, so let's start with the first layer, the first index, the key that is like any kind of string. So let's call it a translation ID key. And as we know, it's a string that is anything. Okay, and now we know that we need to call the mapper on each specific language, like language type. So we could like specify that the English is returning string, the Deutsch is returning string, and the France is returning also a string. And now if we would hover, we see that the function is properly returning a string, something that we want. Okay, so we want to have a content translated. Okay, but maybe it's not really efficient to define things like here. And in the theoretical part, we covered it. We can use the in keywords with the union type to simply reduce this boilerplate. So it will be a lang in language type, and we are expecting it to contain a string. And voila, translation mapper is done. As you see, it has really nice indication what is the shape of the object. This is also like something really useful because you can provide a really good explanation of the keys, what these keys are. Are they like IDs? Are they names? Are they specific languages? And it's much more transparent when you use it as a user or as a developer that forgot what he was implementing there 3 years ago. Yeah. And this is how we would do it here. Okay, and one more thing about the generics. Let's say we need to handle that we may be missing the translation and we return null. No problem, we add it in one place and everything is updated. So this is really useful to reduce the number of changes that we need to do in the code in the future, just relying on the proper generic object types. Of course, we can move it, like we can create this mapper using record. So this would be, okay, so the record and the first key is the type of the key. So it will be string for the first layer and it would contain this value. Okay, so let's copy it. But here we see this also a generic type of object. So we can use another record as a value of the record. The key will be this time language type and the value will be a string. And this is the equivalent of this type. It's a little bit less coding, but you must ask yourself what is more readable for you as a developer and pick whatever suits your needs the best. Just telling you about possible solutions for this one. Okay, so the next example, we need to define the accepted pets config type. Okay, so let's look how we are using this. So, okay, I see that we have some kind of like the species of the pets, and we can create a config that's based on this species, but it's not always true. It can be a boolean, but we are not really using all of the species. Okay, so how we are gonna do this? So as in the previous example, we're gonna use the union type to reduce the key, like to reduce the boilerplate of creating the keys. So there will be a pet, and a pet will be pet in pets. And we are using it, and now we know, okay, the values are optional, so I'm gonna use the question mark to mark the values optional, and there will be a boolean, either true or false, and voila, we done everything properly here. How it would be done using record type. So let me copy this one, add the R for comparison. So it will be a record of pets and boolean. But the problem here is that would mark that we need each of this key be present. Like, of course, I could do like this, but it will fail because it would expect the cat to be either true, false, but undefined. So this is the difference like between using the question mark and undefined. In most cases, you are rather picking the question mark, not the undefined as the part of the tuple. Not a tuple, but the union type, sorry. So how we are gonna fix it for the record? We are gonna use the partial utility, and this set of utilities and when to use them, how to use them, I'll be covering in second part of the tutorial. Okay, so this is the equivalent of the previously typed config. Another example is exercise number 5. Create a function type that will handle the response. Okay, so we're creating some kind of handler that is accepting items and returning something. Okay, so let's analyze this function. We have the response handler, the items, sum of the items. So this is totally an array, and the item should have the key access. Okay, so let's go with the arrays. So there will be an array of object, and the object should contain access key. True? Not true, sorry. It will be Boolean. And we are checking it. So the return type will be a Boolean. So we are finding the item from all of the items that has access as true. So the request is the function should return a Boolean as the result of the operation. Okay, and we see that there are no errors in our code. But maybe we could solve this problem in some other way, because we are fetching the items from some kind of external file, like the external import. And maybe we would use this to make our handler specific for this kind of items. So let's say that we then modify fetch items. Okay, so we have a fetch item. This is returning some kind of mock data. And let's say we change on the backend the access to be simply a OK value. And let's change the mock here. Okay, so what happened now? Oh, we have the problem because now the items is not really matching. So the fact that we took care to properly type the response handler here is making us really like, okay, but it's not really matching. How are we gonna mix it? Maybe I need to map the OK to some other values. What we could have done here is to use the lookup type to get the type of the items. It will be an array. Maybe it will be changed in the future to the set. We don't know, but we can extract this type from the fetch items result type, which is the expected result type from this action. And when we do this, instantly the TypeScript will say, okay, there is no option in number, like there is no access key inside this expected item here. You can then replace it with OK, like the IDE is gonna suggest what kind of keys you're expected to use here. And let's say we will go here again and remove this and create a set, not an array. And what then? Okay, so I need to create a new set here, but I'm gonna create a new set. And bam, here I know that the items on set, there is like nothing like sum, but maybe I can create for each function and iterate through it, or use entries to get the iterator through the entries to find something. TypeScript will really help us to figure out how to do it properly, whatever we change. So let me roll back to the previous changes. I'm not gonna focus on how to solve this problem when the items would be a set. But yeah, this is why the TypeScript is so powerful. It's helping us to solve the problems, and even like in the specific places if we use the proper like approach to the type system. Okay, so once I cover this, let's go to the exercise number 6. And this exercise is all about like thinking about the intersection of the objects. And as we covered, when we're talking about the intersection of the objects, we need to focus on the intersection of each of the keys. So in type A, key X is a string or number. In type B, it's a number. So when we are trying to create the object that will both satisfy type A, type B, the intersection of key X will be only number. we cannot pass the string there because it will not satisfy object B. Just simply, it will not satisfy it. For key y, we've got number here, and the second one is like optional number. So what is the intersection? It will be also a number, because we cannot make it optional, because type A will not accept this key to be not present. And for type B, we have the optional key Z, and it's not really existing in type A, so we'll simply, in the final type, this will be taken straight away from type B. So yeah, this is how we should think about the intersection of object types. Okay, so this example is all about working with your IDE to to understand how the TypeScript is narrowing the types in the union and how it's like dealing with the union types of the objects. Okay, so we have type A, which is an action of post, and will contain a value of number. Type B is action delete, but the values are like more complex structure containing some kind of arrays and stuff like this. This function is really returning randomly either type A or type B. So we have a tuple. This is why this example is all about, what this example is all about. So let's not focus on the implementation of generate action function. What is the most important that we call it, and we get the action and value as a separate keys with destruction. Okay, so when we cover the action, we know it's either post or delete. The same way goes with the value. It will be a number or this complex structure that we have for type B. But interesting, what happens when we narrow the action? So here we know the action is delete. The value then is instantly narrowed down to be an array, because we know we are inside type B in this branch of the code. So what we can do here safely, without mistakes, call, for example, reduce, or simply call length of the array. In else branch, we know that what is left, it's not a type B, it's type A. So we know the value is a number. So there will be no problem to, let's say, calling to exponential. TypeScript is taking care, so we do not need to think about like every aspect of this types. It will simply help us to use the proper values. Okay, so the last example is about the topic of additional keys, what is going on when we are adding additional keys to specific type object definition. And here with the first one, okay, we are creating favorite author with the auto type, and this is how the TypeScript is thinking about this object. We say that this object is an author type, and whatever we in the code pass this object, it should work with the author type. So from the TypeScript perspective, why are we passing this age? There is no need. Everything will be handled properly because it's expecting to be an author type. We are only like adding these values unnecessarily because it's never gonna be useful inside our code base, because it should be always an auto type, no age key. So what we can do, we can remove this key. But let's say we need to have this key there. So we can extend, like use this intersection and extend the definition with age as a number. But really, the TypeScript will infer this by himself really nicely. Simply remove this type. Here, of course, when we are using the spread operator, there's no problems. The problem with the TypeScript is when we have the full control about the creation of the object, then the TypeScript will encourage us, by throwing an error, of course, to not provide anything additional. But when we are using the spread operator, he will not complain. But simply, we don't need to do this. Everything will be inferred properly by the TypeScript by its own, it will then, what is important, then it will check if what we are passing here is a good value for display author function. So as I said multiple times, and I will probably say it more, let's not over constrain our code, simply relying on the infer types for the TypeScript when in the places where it's doing it properly. Sometimes we need to help it, but in most of the cases it will be done by it properly. Okay, so that was the last example from the objects, and the next part will be about the types versus interface. There is a second way to define the shape of an object in the TypeScript. In the past, there used to be differences between interfaces and types. For several years, this has no longer been an issue. In most cases, switching between these two methods won't cause any problems. Let's take a look at the interface. The syntax is almost identical, but we use the interface keyword instead of type, and we do not use equals character. As I stressed before, these two methods are interchangeable. Variables will always match, regardless of whether we use type or interface. This is the follow-up of the concept of duck typing. The object type itself is not important. Rather, the object should support all methods, attributes call on it. We can use intersections for both types and interfaces. There is nothing new here. To create an extended interface, we use the extends keyword. Here are a few examples of this syntax. There are limits when it comes to extending types to create interfaces. When we are having a union type, we can use intersection syntax for types. However, we cannot extend a union type to create an interface. Declaration merging at the most basic level joins the members of both declarations into a single interface with the same name. We can think of this mechanism as an option to extend already existing interface with new properties. This mechanism has more features, like namespaces or providing an overload list, but they are not important for this part of the tutorial. What is important is to remember that interfaces provide this option for interfaces that you declared, but also for the interfaces that are from external sources. As two approaches to define object types has almost the same features, it is good to select one and stick to it inside your codebase. The TypeScript guide suggests using interfaces. I personally prefer types. Caution: this section of tutorial is a subjective opinion. You can have a completely other approach in your type system. I choose types as I don't find interface merging helpful. I consider this feature even harmful, as I prefer to know exactly where new keys come from. I treat this feature as a dangerous side effect. There are two cases where I use interfaces though. I choose them when working with Node.js backend services, which I built using classes. Unless dealing with classes and their implements keyword, I do not use interfaces. The second situation is where I would consider adding interfaces, is building a reusable and a publishable library. If there would be some part of the data passed into libraries utilities that would be customizable by the user, this data I would mark with an interface, as it would be, by design, extendable by the user. An excellent example is using the passport library. The user can define their definition, how to populate the user value based on the different authentication methods. When I was creating a custom middleware, I wanted to know that the user has a specific keys like ID or username. The authors of Passport foresaw this need and defined the request interface containing user, which was also implemented as an interface. I could utilize the merging to have everything defined that the request object contains user with ID and username. This is where I found this feature really useful. We are aware now of the second way to define the shape of an object. Let's practice using interfaces in the examples. The first exercise is pretty easy. We should change the type to the interface. As their usage is almost interchangeable, the same is about their syntax. They are almost the same. All we need to do is to replace the type with interface and to remove equal sign. And here we go, we did the first example. As I said, changing it back would be also pretty quick. let's stick to one way we define object shapes inside our code base. The second example is more complex and it's a little bit ahead of the next parts of the tutorial. But in the standard examples, when we're talking about the declaration merging of interfaces, the examples are pretty, like I would say, idiotic, because we have some kind of interface A with some kind of variable X, and just in the same file underneath there is like a definition of interface A's again with a Y as the string. Like this is the example of declaration merging, but when we have the access to this in the same file, why don't we simply do something like this? So that's why I wanted to share with you how the declaration merging with interfaces works. And for this, I needed to add this part of the declaring module. This is simply allowing us to override, to extend the interface that is created inside this, let's say, external lib. Of course, this is our file in our code base, but we are like handling it like a namespace. So in this namespace, there is this interface, our request type, and it was created so that we can like do whatever we want with this request in the middleware, and maybe to have the option to extend it with new features. So here I'm gonna start the declaration merging part. So I'm gonna use the same name of the interface. As you see, now I can define new properties that will be like handled properly with this same interface here. So this is the function that is using this our request type from this external library, and we are trying to assign the user. The user is not really expected there, so we need to define it. So what is gonna be the user? So the user will be an object containing username that is a string. But before we execute this handler, the username is undefined. So we need to remember that in this interface, the user is undefined. So the proper shape will be the user, with the username being a string. Of course, not a string as a number, but as a type. And here we go. We extended the request with new properties, solely because it's using the interface, which is open to declaration merging. And this is one of the examples where the interface really makes sense. Here I can, of course, like create an X that will be a number, and then our code will complain, okay, we're creating a user, but we forgot to add X. So yeah, we have a type safety in our system, even if some of the data is pushed through external libraries. And this is like one place that I am personally considering to use interfaces for. The next part will be covering the TypeScript keywords, so we'll learn a little bit more of the specific usage of keywords in TypeScript. This part of the tutorial will focus on language-specific keywords and their usage inside TypeScript. We will start with the as keyword. It is a keyword you can use to cast one type to another. This is sometimes useful when, from the code, we know that this specific type of variable has a more strict type that it can be automatically detected. The example on the screen shows how it works. The object keys return by default array of strings. Here we know that the keys can be more specific. To force this type, we are using as casting. Another example shows loading data from local storage. Let's say we can be sure about the content that is already saved there. Again, we are using as keyword to have a nice type support for cached value variable. We can also use angle brackets instead of the as keyword. This way of casting is rarely used as it interferes with JSX syntax. In most of front-end application, you will not see this type of code. Using as exposes us to the risk of invalid code handling. That's why it should be used only as an exception and last resort. Also, TypeScript has a safety feature that prevents casting a variable of a specific type to a type that doesn't match at all. Unless you are writing a test that expects to fail, don't use this feature. Better fix your typing system for the future. Combined with as keyword, any will help you fix problems with typing when TypeScript itself is not able to deduce the proper type of the variable. In most cases, falling back to using any or as will indicate that something is not properly typed. In some edge cases, you can use these keywords to work around errors. Their usage is common in generic functions. Any keyword marks a variable that can contain any type of data. TypeScript will not complain when you will try to use a property that, for example, is not accessible in subtypes. Using any neglects all of the benefits provided by TypeScript and should be avoided if possible. It's just a fallback to plain JavaScript with its full freedom and no type safety. Unknown is a safe version of any. This type indicates a variable whose shape we cannot be sure of. This keyword is excellent for marking the value of the response from external sources, like user inputs, local storage, or some external APIs. TypeScript, in contrast to any, will not allow you to use properties or methods of unchecked variable. It will force you to write code that safely handles any type of input. There are some dedicated libraries that specialize in checking safely the proper type of unknown data. Two examples are Zot and Yup libraries. On the screen you can see how we can verify input data using Zot schema validation. The keyword never marks a variable whose value will not occur, no matter what happens. This feature does not make sense from the code perspective, as we are not aiming to write non-executable code, but it can be used to detect incompatibilities. TypeScript will detect problems with the logic by finding out that the output will never occur. Here we have a union type with two actions. When we check both of them, there is no other option left. The checker will complain that we are trying to execute code referring to unreachable, never existing variable. We can utilize this feature in some specific scenarios. Let's look at this example. We added to the previous example a third possible action. The code is working fine, but we forgot to write the handling of a new option. If we were writing this part of code and we would like to force during the development proper handling of new features, we can add the following piece of code. This line is never intended to be executed. If we were to add a new action, the never variable will be trying to receive a new action type, which is a string. The compiler will report this and raise an error. The developers will be forced to cover new options. This is rather an edge case, and this pattern should be only used in the specific places inside your code. I wanted to show some practical usage of never keyword, not only the fact that it will appear inside error messages where we are gonna mix up incompatible types. The keyword typeof enables us to extract the type of the variable. This is useful when we don't want to create a boilerplate or want to extract the type of an object or a function from external library. Like here, I have a defined object and would like to reuse its shape as a type. I can use typeof keyword to extract inferred type from static code analysis. As this mechanism works on the static layer, it has its own limitations. Do not expect that TypeScript will adjust type to the real object during execution time. When I was starting to work with TypeScript, I made this mistake quite often. Let's say we have a function returning some mixed return value. We may know better what is the result of the operation. Here it will be success true, value 20. TypeScript is analyzing only the static code. Using typeof here will result in union with either success false or success true with value as a number. Typeof keyword is extremely useful when we are dealing with external libraries that are not exporting their internal types. We can use this keyword to extract exact type of, for example, imported object or function. Then we can use it, for example, to type properly the arguments of our own functions. Like always, we have an example for this. We are importing parseItems function. We want to create our own function, which will accept callbacks of the same structure like imported function. For example, we want to use it as a default handler, but let's say allow also some kind of custom implementation. We are using typeof keyword to extract proper type. Keyof operator enables us to extract keys of the object type in the form of a union. This can be useful to reduce boilerplate for actions such as object mapping, index signatures, or adding arguments inside functions that require the key of a certain object type. Typeof and keyof can be used together. At first, we are using typeof to extract shape of the feature config object. Now, when we have an object type, we can use keyof to extract keys from this type. Caution: this specific keyword is used on types or interfaces, not variables. Here, our keys will be a union of SEPA, summer sale, and winter sale strings. Now we can use our newly created types to prepare a function that will safely access our features configuration. You should pay attention to the benefits of this approach. Imagine I will remove one feature flag. TypeScript will instantly check if there are no methods using this removed key inside our codebase. It will throw an error if our cleanup was not done properly. Combination of proper patterns and keywords creates a developer-friendly environment, which is not only increasing code safety, but also boosting refactoring. We will use keyof in great numbers when writing generic templates and functions. The last keyword I will cover in this section is asConst syntax. It can mark some value as immutable. This is really helpful for the TypeScript when dealing with objects. Instead of JavaScript, they can be easily modified even when we are using const to declare them. There are 3 common places where you can use asConst to make the type system better inside your codebase. First is marking object as constant. This helps TypeScript to access with confidence keys and values of such an object. Look how adding asConst changes inferred types in the presented example. The second option is to mark the keys value as const. The example will explain the concept better than description. We have a function that expects 2 specific languages. We create a proper object containing a proper language, but the TypeScript is throwing an error. That's because it's not going into details about the specific values and assigns a general string to the language key. Marking language as const will make this inferred type to contain specific word as keys value. It's not expected to change over time, so there is no use assigning general string as its type. The last option is to use asConst to mark an array. This will make it read-only, and you should rather use tuple instead. asConst make items and an array read-only, which is much stricter typing, and you will probably not be able to use these variables across your codebase, as the read-only values will not match standard mutable types. I want to mention one additional keyword, which was introduced recently in TypeScript 4.9. The purpose of satisfies is to enforce a constraint on a variable without changing its type. This is super useful when used to define mock objects, part of which can be accessible separately without losing their exact structure. I will show you how it works in this example. I created an external file containing 2 mocks of resp type. One of them I will mark using standard type definition. For the second, I'm using satisfies keywords. Both of the mocks will be checked to match the expected type. In the second file, I'm importing resp type and both mocks. I'm writing 2 functions that are simulating some unit tests. The first one is expecting to receive resp type as an argument. The second one is expecting to receive data from success resp type. Both mocks are the same, but the standard one is reported by the TypeScript to be invalid input for the second function. This happens because the TypeScript is not keeping the exact type of the variable. It knows that data key is not always present for this general type. But when we are using satisfies keyword, magic happens. The TypeScript is remembering the exact shape of an object and knows that it contains data key with proper value. Satisfies provides type checking while keeping original value intact for other types checks. Now, as we know more TypeScript keywords, let's practice their usage inside the exercises. Okay, so as standard, I will remove this unknown to have the marking of the stuff that needs to be replaced. And let's start with the first example. Okay, so this is an example of usage of as keyword. As I said, I recommend avoiding usage of it at any almost cost, unless we have like a specific cases. Let's say we want to practice using it on this example. So we have a function that is accepting the number. If the number is below 0, it will return undefined. Then it will return the database connection string. And we are calling this function with value of 2. And we know that the result will be a string, but the TypeScript will try to force us to handle the undefined value. And what we can do here is to use as keyword to overcome this problem. And we will simply mark this return value as db connection string, like this. And the TypeScript is no longer complaining, but we can also really make like fool ourselves that is something else, and we will not really detect it. So as I said, use as keywords as the last fallback. It's not really safe, it's not really worth it when you start to use as in many cases, unless you're writing some kind of generic function, which is, I would say, an exception. You start to lose control over your type system, and you're making your code much more dangerous to modify. Okay, so the next example is about using unknown keyword to force safer approach to the code. Here we are looking at the local storage, and we don't really know what is there. That the JSON parse is simply returning anything, and this code is executed correctly, but maybe when we put some kind of, I don't know, an object string, like parse object string into the storage, it would crash. So what we can do here is to mark the return type as unknown. Then the TypeScript will think that, okay, data is unknown, so I cannot really use to uppercase method on this because I don't know what is it. And it forces us to check if it's a string. So I'm gonna use typeof keyword to check if it's a string. And I will be covering in the next part of the tutorial various ways to check the type of the variable and do it safely and avoid any edge cases. So the typeof is one of the ways to do this. Okay, so let's move to the next example. This example will try to show the narrow edge cases where we can use never keyword. So we have a function called what does the fox say, and it's working fine. But let's say we finally want to cover the fox, and we add the fox to the proper types of the animals. But the function is, the TypeScript is handling that, okay, everything is fine, but the function for the new animal with a fox will call the tweet. It's not really working properly. It will not crash, but is it working fine? I would say no. And for some examples of the functions, we want to force the developers to handle every example. So let's comment it out and change this function to be more safe. So this is the way I can use the never keyword to do this. So I will check for the bird and return tweet as well. And then this is the snippet I was talking about during the theoretical part. So I can create a variable that will be a never and assign a value of the animal here. This is proper because this, after all of the checks, animal here is like never. It should never exist. And we can throw new error. I will not really work on the error message here. Let's say it will be an animal. And okay, we added maybe not so useful 2 lines of code, but what happens in this, let's say, really important part of our code that should be handled every time and every developer should take care when adding new option? What will happen if we are gonna add a new animal type? TypeScript will start to complain. So we are not gonna tweet for the fox. We're gonna be forced to cover this example again. And what does the fox say? I have no idea. And so this is how we can use the never keyword to make our code safer and really narrow specific edge cases. So let's go for the next example. Okay, so this example is all about usage of typeof that can be used to extract the type of the existing variable, object, function. So we are creating some kind of function that is a response handler, and we are passing the fetch data. This function is important from external library. We don't have the access to the type of this function, but we would like to use it as an argument of this handler response and use it properly. So call with proper values. So here we are gonna use the typeof to extract the type of this specific function to get the general type of the function. Okay, and now TypeScript is telling us, okay, something is not right. You should call this function using URL. Okay, we have the URL, but now, okay, I need to define some kind of parse function. I will not really think about how it should be done. It's simply the example how to use the typeof. So let's say we have the response, we need to return a string. So let's go with JSON stringify of this response. Not really important here. The important here is that we can use typeof to create a type, and it will match the imported function from the external library. Okay. So the typeof can be used both with keyof. So the keyof is the way to extract the keys of the objects. So we can use the typeof also to extract the type of imported object. So as we see here, we want to have the function that was extracting the parts of the personal data. And the personal data is an object imported from the external library. And we don't have the type of this. So like trying to come up with, okay, so there will be name, surname, birthday, maybe it will change over time. We want to extract the list of the keys from this personal data object. So the list, of course, will be an array, and how we can access the keys of the personal data. Okay, so we need the type for the first. So to get the type of the personal data, we are gonna use the typeof personal data. And we need the keys of this type. So we're gonna use the keyof before the typeof. And like here, we don't need these brackets. This can be like long line keyof type of personal data. You will probably see lots of times this kind of structure. And as you see here now, everything works fine. And when we try to access new keys, we are gonna be forced to you pick from the existing keys. We cannot like access and add something non-existing here. TypeScript would warn us if we would do this. Here, there is one thing I want to mention. This function is not properly typed, so this is not really helpful function. I will be covering this in the example of like extreme template system. And this will be in the, like, I think the last part of the tutorial. So let's not focus here that this D1 type is not really proper one. It should be like picking the name from the existing keys that we are passing. But it's not really important here. Here in this example, the most important part is that we can use a keyof to extract the keys of the object type, not the object as a variable. We need typeof before. Okay. So the last example is about the satisfies keyword. So let's see and what we have here. So the first one, for the first mock using satisfies, we can access data pretty easily. For the standard mock, the response type is not allowing us to access data. And what's funny about this one is that the both objects have exactly the same values. The difference is how we are constraining this object to be a response type. Here I'm using the satisfies keyword to do this, and here I'm using like a type definition of the variable. Both of these ways like prevent me from adding something extracurricular or forgetting about some kind of keys. So both of these ways I have a check that these values are properly created. But when we are using satisfies keyword, it's preventing the shape of the object. So we can add access, for example, data, which is not generally available in the general response type, because like we have this like error or error like second option in the tuple. So I'm really glad to use satisfies keyword when I'm defining the mocks for my unit tests, or for example, to mocking the responses for the storybook, because I want to access all of the levels of the mock. And I really encourage you to use this specific keyword for these examples. So as we're ending with the examples for the TypeScript keywords, the last thing that we're gonna cover in this part of the tutorial will be enums. So let's go to them. Like lots of other programming languages, TypeScript offers enums. They are a special data type that enables for a variable to be a set of predefined constants. This data type is a little bit different, so it has its own chapter inside this tutorial. There are three types of enums inside TypeScript. The first one is a numeric enum. The values are numbers. By default, the countdown starts with 0, but we can also assign custom values for selected items. The string enum contains strings. We define it using the following syntax. We are not limited to one type of value. We can also create mixed enums. After we create an enum, we can access its values using dot syntax. Enums can be at the same time used inside type definition. One thing, both for code and type system. Like in this example, we can use direction as type, but also use direction.up and down inside if statements. There are a few limitations to enums that can be annoying during development. That is because they are not bound to existing JavaScript primitives. There are a few cases when the way enums works is not entirely intuitive. We created an enum direction and object which contains this kind of value. When we are comparing a string enum to string, the code looks fine. The moment we are trying to assign the same string value to the key, TypeScript will report an error. This situation does not exist with numeric enums. Why is it a problem though? Let's imagine that we are using enums to define part of backend API response types. We copy the JSON response from the server to use it inside our unit tests. But TypeScript will complain about the values, as copied strings cannot be assigned to enum values. We will be forced to replace, every time, proper string responses with corresponding enum values. When there is a problem, there is usually an alternative approach. We can utilize the power of asConst keyword to create a similar solutions to enums, which will be also working fine with strings, while keeping the same level of type safety. This is how it's done. We create an object that will represent enum-like value. We mark it as read-only using asConst. Now goes a magic formula. I will try to show you how we are creating it step by step. The type of direction object is object with read-only keys. Using keyOf on this type, created using typeof syntax, we can extract the union containing the keys inside this object. Here it will be up, down, left, right, but in the camel case. We already covered in this tutorial lookup types. Just a quick reminder, they can be used to extract types of specific keys inside object types. When we would use lookup for type of direction, we can extract the values of keys. We had a union of keys in the previous step, so all we need to do now is to combine this into one big formula. This is how the final magic snippet looks like. We don't need to remember how to reproduce this type generation every time. Let's just copy and paste the existing types and replace the source of value with different asConst object. Let's compare now how different it is from using normal enums. As you can see in the example, we overcame the problem we were facing with using enums. we can use the same syntax as previously, using dot notation on standard JavaScript object. This also means that we can use such defined types to mock responses, and they will accept not only references to the original object, but also normal strings of proper values. There are of course some costs. The syntax is a little bit longer than for enums. We must import separately type and object. Enums could have been used both as value and type. Enums has better inferred type support. When we are creating an array containing some values, the inferred type will be an array of enum. For an alternative solution, we will be forced to mark the array with proper source type to have the similar experience of type checking. This will be the last practical part of the tutorial inside this video. So the last thing we are gonna work on for now are the enums, and let's go to the exercises. So for the first exercise, we should create an enum that creates the enum of the supported systems. So let's copy the values, and the first enum is a number enum. So we're gonna simply remove this value, and all we need to do is add the comma at the end. And yeah, the default value will be 0, and the next item will be 1, and the next one will be 2. We can assign some kind of values, but whatever. The number enums, this is how we create them. So for the string enums, we're gonna create the keys in the same way, but what we need to do is define the values of them. So let me copy it, and we simply need to provide some values, like a string values for the enums. Of course, we cannot duplicate, it will not work for us well, so let's add the unique values for each of the enums. And yeah, this is how we create the enums with the numeric enums or string enums. And let's go to the second example. And the second example is not about the enums, but the alternative way. I talked about it a bit on the theoretical part. So let's see how we can change this code to be more friendly to the strings. So as you probably remember, we need to create an object that will contain the same stuff that we have here. So I will call this object customer. I like to use the capital letters when I create some kind of things that are not supposed to be changed, like the constants. So I will follow like this. And as you remember, we need to mark this object as immutable. So I'm gonna use as const. So now we're not gonna rely on the enum, but on the type. So this is where this magical snippet formula comes in. I was covering in details how this formula really works out for us, and what is the idea behind all of these steps of this magic snippet. But at the end, we get the type that contains the values of the customer. And as I mentioned before, there are some drawbacks. And here, for example, we cannot access the type anymore as a value, what was possible for the enums. I will replace this with the customer object. But what is important here? It is no problem to use the string values. So let's say we create this payments list by the response from the API. We can copy paste the JSON and everything will be fine. No need to replace stuff, no need to import the enums. It will be working properly. So I really like this option to work with the limited numbers, like predefined sets of numbers. I'm just really avoiding enums. I'm going for this as-const solution for the objects. And that will be the last part of the exercises and the end of the first part of the tutorial. In this first part of TypeScript 0 to Hero, we gain lots of basic knowledge. We will continue our journey with TypeScript in next parts. We will focus now more on practical solutions and patterns that build scalable and responsive type system. See you soon!